we have lots of A to D converters, but also lots of applications, because as you can see, each block is a different kind of application, going from slow is on the left side because you see 1 hertz, 1 kilohertz, 10 kilohertz and so on, all the way to 10 gigahertz. The highest speed A to D converters you will find for digital scopes here, where you only need 5-6 bit resolution but very high speed, and you see all possible applications in there, going to DVD audio, going to more than 20 bit for example, but not too fast, 20 kilohertz. You see all different kind of applications. Going to low power, and the portable applications are here. I will show you several A to D converters made for this area, medical applications, portable stuff, all the way. No, I don't know a 1 kilowatt A to D converter yet. May come. Now, we are going to compare all of them using a figure of merit, as we have done for operational amplifiers, indeed, containing the same ingredients. And I've added a little example. As you can see, I couldn't resist the temptation to do that once, just to put in some numbers to indicate that indeed we have various kinds depending on the resolution, here bits, and now speed or conversion rate is vertical. And they are put together in what's called a figure of merit, which is the power that you need to reach a certain speed, which is 2 times the bandwidth, and then the number of bits that you reach for that bandwidth. This is the effective number of bits, which is nothing else than the signal to noise and distortion ratio, minus a little bit divided by 6. So for example, if I need 1 milliwatt to reach something like here 10 megahertz, 5 megahertz bandwidth, what we need 2 times, Nyquist says we need at least 2 times the bandwidth, so we take it 2 times for 10 megahertz, then this is going to be, what are watts divided by hertz? They come out to be joule. Okay. Now, if this is joule, what is this? This is the number of steps. That means that if you have an effective number of bits of 10, then 2 the power 10 is something like 1000. It's a little bit more, huh? But that means that picojoule divided by 1000 is going to give you femtojoule per conversion step, or conversion depending on who is talking. So this is to indicate that we will compare all those A to D converters, how efficiently power is used to generate speed and resolution limited by noise and distortion. We will compare them with the same figure of merit. And I can show you some examples. This is again bits resolution versus frequency, as you can see. And you see which kinds are surviving in which area. Huh? Those are all picked from famous speakers who are explaining which kind of converter can be used in which area. And we will discuss all of them. I'll show you some switch capacitor ones, but we will spend a lot of time on successive approximation ones. Oh yes. And we will talk about n-step flash, for example, and flash itself. They are the ones that go to higher frequencies. Huh? You see the gigahertzes here, and the combination of pipeline and flash, and in the middle we have sigma delta. Sigma delta is not for today. That's for next week. You'll have to come back next week for sigma delta. So all the other ones we'll do today, and sigma delta is for next week. And you see that this is in the middle. It's a good combination of bits, not too high in frequency. Actually, the highest frequency one is 30 megahertz here for 12-bit, which is used in second or third or fourth generation ADSL. So that's about the maximum that you can get today, and I'll talk about that next week. And the other ones is for today. Now, the person or the information about how far you can go today, you can get from this website. You should try it at least once. You get all those numbers and then nice graphs, and I've copied one of them for you, indicating that indeed when I look at that number in picojoule here, the power divided by 2 times the frequency, remember, and this is the signal to noise and distortion ratio. We see that indeed we have lines corresponding to, this one corresponds to 100 femtojoule per conversion step, and this is 10. And you see some people go even further. This must be 1 or something here somewhere. You see all those little dots corresponding to conferences. And actually the last ISCC, sorry, not the last one, the last but one, ISCC 2009, gives you all the red little squares. At the end of my talk, I will show you the ones of last week's ISCC in San Francisco. You will see how much further they go. The main thing is to see that indeed that the higher resolution, the more power we need for the same frequency. Or for the same power, you can't get the same frequency, which is normal, of course. And we'll try to calculate this kind of a curve. So this is comparison of papers which have been presented on various conferences, but especially the ISCCC. And a similar thing can be derived saying that, well, what in communications, for example, you can say that this is about constant. I will comment about that later. This is not really that constant. And indeed, if you increase the bandwidth, you will lose the resolution, which is the same kind of curve as on the previous one. Illustrated by many communication systems. You recognize some of them. Your GSM, for example, that second or third generation ADSL, ultra-wideband, for example, they are more or less on this line. But it doesn't quite go like this. I'll come back to this curve at the end of my presentation today. Now, this was just to warm me up a little bit, very shortly. Now let's have a look at what we're talking about, and then let's have a look at most kinds, and I will spend most of the time on, not the integrating one, no, on the SAR, successive approximation one, and I'll talk a lot about the flash one, for example, including the interpolating and folding, and of course pipelines too, and at the end I will have a similar comparison, figures of merit, etc. Okay? That's what we will do. First definition. The very first definition is simple. An A to D converter, what does it do? It's going to convert a continuous range of voltages between 0 and 1. This is not 1 volt. This is the reference. That could be 1 volt, could be less, depending on what kind of system you have. Or 1.2 volt, this could be 1 volt. And this is a continuous range, and it's going to be converted into a discontinuous set of steps. You see that, for example, if I change the input voltage, I step from this value to this value, and then to this value, and so on. And actually, we have to do that in a very irregular way. Those are the red dotted ones, but that's not always the case. Sometimes my staircase is not that regular. We have mismatch, we have all kinds of side effects. So that means that we have something, we need somewhere a parameter to characterize that my staircase converting a continuous range of voltages into digital code is not that regular. The same for a DAC, of course. When I have numbers coming in like 0, 0, 0, 0, 0, 1, and so on, and so on, and so on, I expect voltages to come out. And again, the red dotted ones are the ideal regular ones, and there may be some deviation. So we need some numbers to characterize that. Well, what we are going to do first is to say how many steps we have, and the number of steps is simply given by the number of bits, meaning that indeed, when I work with a reference, so a voltage is going to be scaled by a reference 1 volt, for example, and then the code is going to give you, the digital number is going to give you how much 1 over 2s I have, maximum 1. Those are all 1s or 0s. It says how much of 1 over 2, 1 over 4, 1 over 8, 1 over 16, and when this is 10-bit, this is 1 over 1000. So that means that we have converted a voltage into a number of voltages, voltages, which are indicated by digital code by B. So the smallest one is called the least significant bit, and the biggest one is going to be the most significant bit, and especially this one is important. It says what is the smallest step that you have in this staircase, converting a continuous analog signal into a digital one or vice versa. So the number of bits is the resolution. Now, when you do that, you see immediately that converting a voltage into a staircase gives you an error, because here we have a number of steps. So the difference between the analog original signal and the quantized signal, where we just follow the steps, is going to be the difference between that red line and those steps. And when I look at that, we see that indeed this is maximum here, it goes to 0. This is go to maximum negative and goes to 0. So it's maximum here and goes to 0, goes to the maximum negative voltage and goes to 0. This error is a quantization error. And the quantization error has an RMS value. And this is the error that you have on top of your signal that's going to give you the signal to error ratio. And we can calculate how much that is. We call that noise. Actually, it's not noise because it's predictable. And as you know, noise was unpredictable. But this is predictable. We can calculate what the RMS value is. So we take the square, the integral of that. We find that indeed, if the peak value is delta from peak to peak, from there to there, if the peak value from there to there is delta, And delta is nothing else than my peak-to-peak voltage divided by 1000 steps for 10 bit. Del delta square over 12 gives me the quantization error. And, of course, once I know how much the peak-to-peak voltage is, then I know how much power goes in that signal is the V square over 8, and I can calculate the signal-to-noise ratio. It is a quantization noise. It has nothing to do with thermal noise. That comes later. So now we will look at the signal-to-noise ratio for a quantization with n bits, like 10 for example. We find that the signal-to-noise ratio is simply the ratio of this to that. And we can easily calculate that. And we find that indeed signal-to-noise ratio is this, usually written in terms of dB. When we take dB, we find 6 times n and a little bit, about 2. So that means that if we have 10 bit, we can expect something like 62 signal-to-noise ratio. Signal-to-quantization noise ratio. And that's an expression we are going to use all the time. That was also the expression which was used in that figure of merit, of course. To convert bits into dBs is easy. Okay. Now, what are the two numbers that characterize how regular our staircase is? What are the two numbers? We have two of those. The first one says what is the maximum step that we ever get, which is a local effect, and the other one is kind of a global effect. First, the local effect. When you look at this here, you see that clearly that this is a much bigger step than all the other ones. Normally, we expect only something like this. And now we have something that is much bigger. It's too big. The difference between that one and what we normally expect is called the DNL, differential nonlinearity. It's a differential. It says the difference between one which is way bigger than this one. So that difference here, and we have to subtract the small one, which is this one, gives us the differential nonlinearity. What is going to cause that? This is a local effect. That could be mismatched, that could be a gain which is not right, or whatever. All local effects are going to do this, and mismatch is the one on top. But there is also another one that says, well, sometimes we deviate too much from the average, which is more a global effect, that my curve goes too far away from my average curve, and this is called the integral nonlinearity. It's kind of an integral that says how far, which is this largest distance that I move away with my output with respect to the average. And the INL represents more global effects, distortion maybe, and some other things. So those two characterize how good we have converted the analog signal in that staircase, in that digital number. And we have to quote both of them, and of course both of them have to be small. And small, what does that mean? They have to be smaller than this step here, which is the least significant bit. So when we look at results, measurement results, for example, we will have to check whether the DNL and the INL are both smaller than a least significant bit, because they give you results of local and global errors. And there are some more errors, gain errors, for example, and offset. Everything that we have said about amplifiers is going to come in here because we are going to use amplifiers. Okay? Now, some other things, of course, are characterizing something like this. When we convert a D to an A signal, for example, we will have some distortion when this is the fundamental, and we have some spikes at higher frequencies. Wherever they come from, they could be on the harmonic frequencies, second and third harmonic, if this is the fundamental, second and third harmonic, or mirrored by a mixing effect towards other frequencies, an image frequency, whatever is around, everything that is not at the fundamental frequency divided by the fundamental is going to be called distortion. It will simply be clock feed through 2. We are talking about analog and digital together, so we're going to have clock feed through, meaning that indeed also that has to be included in the signal to noise and distortion ratio. So an easy way to figure that out is when I do a measurement, I have a fundamental here, for example, and you see we have a number of spikes. The RMS value of all that divided by this, or vice versa, gives us the spurious free dynamic range, or signal to noise and distortion ratio, whatever you'd like to call that. So this is an important number to characterize A to D converters. And when we increase the number, when we increase the signal, for example, if we have a small input signal, then you don't see those anymore, because distortion depends more on the input signal. That means that the larger I make the input signal, the more the harmonics are going to come up. That means that indeed for the largest signal, we have the highest distortion. meaning that the larger we make the input signal and the maximum is the reference, this is 0, that means 0 dB attenuation with respect to the reference. 1 volt peak to peak, for example, a little bit less. This is then 0.1 volt peak to peak, 10 millivolt peak to peak, and so on. We see that when you do calculations, of course, the signal to noise ratio goes up all the time because the noise is more or less constant, and the signal to noise ratio increases with the signal. But at the end, in practice, first of all, when you do calculation, you kind of lose a bit in practice by realizing the converter, all kinds of problems. You lose a bit, and at the end, because then we have a large signal, distortion always comes up. So this will be the maximum signal to noise ratio, but this is the maximum signal to noise and distortion ratio. So it's very important when you do comparison to include distortion, otherwise you can't do a comparison. Many people go with signal to noise ratio, and they don't say anything about distortion, which is not the right way to do, of course. So the signal to noise ratio at maximum input voltage is the number that you put in that figure of merit that I've talked about. Now let's start with all the different types. The integrated one, and then especially the successive approximation one. Integrated is a simple one. It takes a long time, but it works very well. Let's have a look how it works. It's used in voltmeters, for example, and when you have plenty of time, it uses one single integrator, and it's used twice, the same integrator, meaning that all the problems of the integrator, limited gain and offset, all that are going to be cancelled out because you use the same integrator 2 times. Okay? So we're going to use it, for example, we apply an input voltage, and this is an integrator. When you integrate an input voltage, what's going to happen? Well, that output voltage has a sawtooth that becomes bigger all the time. Okay? So that means that when we apply an input voltage, we will have a sawtooth. We have an output voltage that simply integrates the input voltage with a time constant RC, and then if we take a constant time, then clearly this contains the information of the input voltage. The slopes are shown on the next slide. Let me show you that. Here it is. So if we take a certain input voltage and we integrate that with a certain time set by a clock somewhere, of course, then we are going to reach a certain voltage. And at the end of that time, so many cycles of a clock, we have a certain voltage at the output of that amplifier. That's the first phase. And the second phase is we are going to now switch a reference voltage in and discharge this capacitance, meaning that now we have a constant input voltage, and now we are going to check when we go back through 0 with the output voltage and measure that time. So in the second phase, we're going to go down with a constant slope. Wherever we are, this slope is constant and set by the reference voltage. And now a comparator is going to figure out, here we go back through the same voltage as where we started, or there. And now the ratio, clearly the ratio of the 2 times is going to be the same as the ratio of the 2 voltages. And that's how it works. The ratio of the 2 times, this one is set by that converter, and this one is also set, this is a reference voltage. So the ratio of the 2 times is simply the ratio of the 2 voltages. And as a result, we have a conversion of input voltage into a time, which is a counter, and we have an accurate representation, digital representation of the analog input voltage into a digital code. So this is called dual slope, because you have one slope and we have a second slope. Of course, that takes a long time, not only to have to charge this capacitor, but also takes some time to discharge it. But it's very accurate. All the problems associated with the amplifier are the same in phase 1 as in phase 2, and as a result they cancel out. And that's the beauty of this kind of dual slope or integrating A to D converter. So when we look at advantages and disadvantages, I can let that run for a long time and have a high resolution. Oh yes, look at this, 16-bit, 20-bit, no problem. High resolution, very linear, same amplifier used twice. It's very simple. You have just an integrator and a counter, that's all you need. But it takes time, of course. We can filter out the 50 Hertz if our clock is a multiple of the period of the 50 Hertz. But of course it takes a lot of time, and that's the thing we have against it. So for a very accurate application, and the typical application is a digital voltmeter, where you have some time, not always, but you have some time. You have to wait a lot of clock cycles before this is over. That means that if you have a clock of 1 megahertz, for example, that takes 7.6 seconds, which is a long time indeed. So the main disadvantage is time. Apart from that, it's beautiful. It is simple, and you get as many bits as you like. That's the first type. The integrated all-due slope A to D converter. It's not used very much, only in voltmeters. What's used much more is successive approximation. Let's have a look at that. What is this? Successive approximation, SAR, as I say. Successive approximation register based A to D converter. Successive approximation register based A to D converter. What is that going to do? Well, first of all, we have to remember the input voltage a little while, because it's going to take a little bit of time to do the conversion too. And what you do, this is a comparator, which is going to compare what's coming back from this input signal. And now what this is doing is actually it's going to figure out whether the input voltage is larger or smaller than what is given back from the DA converter. What the DA converter is going to do, driven by some logic, is to give back reference voltage, half reference voltage, 1/4, 1/8, 1/16, 1/32, in order to approximate that input voltage. I'll give you an example in just a moment. So meaning that if the comparator gives you, for example, a 1, then this is going to indicate that I have to give a reference divided by half first to subtract, and then a reference divided by 1/8, by 1/16, by 1/32, by 1/64, depending on the number of bits. And we try to approximate with this digital number, we try to approximate the analog voltage coming out of this with the analog voltage coming in. So the only thing the comparator has to do with 10 bits is 10 times to try to approximate the input voltage with what is coming back from the DA converter. So that's going to take time. For 10 bits, it's going to take 10 cycles, and that's it. So it's not too bad. It's going to take some time, and it's very accurate too. We will see how accurate. First of all, let's see how it works. A little example here is, I have, for example, an input voltage of 0.4 volt. Input voltage is sample and hold. This is 0.4 here, and that's held for the 10 cycles. We keep it constant. And now we are going to try to approximate the 0.4 volt with a 1 volt reference. How do you do that? Well, the first thing you do is that, the first step is actually superfluous, the 0.4 volt is smaller than 1 volt. That's the reference, that's for sure. So that means that if the 0.4 volt is smaller than the 1 volt, that means that it's smaller than, I get a 0. That's the most significant bit. And I divide the 1 volt by 2. Then it's half a volt. The 0.4 volt is still smaller than half a volt. That's what the comparator says. This is 0.4, So we have another 0 to say it's smaller. And now the logic says, well, it's smaller. We're going to make that smaller again, but now with 1/4. So we go down by 0.25. And now we see that 0.4 is larger than 0.25. It's larger. That means that now we get a 1. And since it's larger, the logic is going to make sure that we subtract, that we add now a reference over 1/8. A reference over 1/8 is 0.125. We add 1.25. But for 0.125, the DA converter gives you 0.375. The 0.4 is still larger than the 0.375. So we have done a comparison with the input voltage with the reference. A reference divided by 2, a reference divided by 4, a reference divided by 8, and it's always added on the previous value in order to approximate. So if this is the 0.4 volt, we first compare that to the 1 volt, then to half a volt, then to the 0.25, then to the 0.374, and etc., etc. So each time you go one step further, there is 1/2 to the end added or subtracted. That's why we need the logic for, to compare the input voltage to the next voltage. So there is a successive approximation of the input voltage by a voltage given by the DAC, which is driven by logic, and it tries to get closer to that input voltage by fractions of the reference voltage, each time with the next fraction divided by 2. That's how it works. How far can you go with this? Well, of course, you have to make sure that this is able to distinguish that analog voltage given back by the DA converter to the input voltage. If you have an offset of 5 millivolt, then 5 millivolt is the end of the story. That means that we cannot make a more accurate comparison than within 5 millivolt. So that's going to be 1 volt over 5 millivolt is 200. That's the number of bits. 200 corresponds to 46 divided by 6. That's something like 8 bit. So we need to have a very accurate comparator in there to do the successive approximation. So that's how it works. The easy way to do that, and this is still being used today, is by charge redistribution. Because how do you do that? It's easy to say I take input voltage 0.4 volt and I compare it to 1, to 0.5, to 0.25, 0.375, 0.4375, etc., etc. But how do you actually do that? Well, the simplest way, the original one. I'll show you the oldest one, I will show you the most recent one. The oldest one was in 75, the most recent one was last week in ISSCC. They do the same thing. They haven't changed much. The only thing that's changing when you make SARs is that you make those capacitances smaller. That's the only thing that changes. And why would you make it smaller? To consume less power. Remember, the figure of merit was power for what you were trying to do. And when you take smaller capacitances, it takes less power to charge them to a certain voltage, isn't it? And then we are going to make our comparator, for example, dynamic, because this one is on all the time. That's the only block that consumes power, this comparator here. Okay? That means that if this is on all the time, that's going to take a lot of power, and your figure of merit is not going to be any good. So the most recent ones go with capacitances, and you see these capacitances represent all those voltage divided by 2 and by 4 and by 8 and so on and so on. So we have the capacitances multiplied by 2, multiplied by 4 and 8 and 16, and this is only 5 bits. Otherwise, this would continue to 32 and 64 and 128. Okay? So those capacitances today are made smaller. For example, in the most recent one, this capacitance is only 1 femtofarad. Have you been able to make in your layout ones 1 femtofarad? You got lots of femtofarads free as parasitic capacitances. We are talking on how to scale femtofarads. And if you can do that and you can make that dynamic, you only use the amplifier or the comparator when you really need it, then you have the best successful approximation, SAR-based A to D converter. And then you have a beautiful low number for the figure of merit. Let's first have a try to look at how it works. It's a switch capacitor configuration. Yeah. So what we are going to do is charge and discharge capacitances. But we have to find a way to do successive approximation. First of all, and this is the first setup, yeah, first of all, yes, the accuracy is going to be limited by how well you can do the matching. And clearly, if this is only a femtofarad, it may not be all that good. If it's not that good, you'll have to do all kinds of calibration, digital calibration and other things. So in 1975, this capacitance was half a picofarad. It has gone down to a femtofarad today. So things have changed. But the very first thing is sample mode. Sample mode means what? You see that the input voltage is going to be put on all those capacitances. We see that this amplifier here, it's closed, meaning that if you have sufficient gain, this is like 0. So the voltage at the input of the amplifier is 0. That means that if you apply the input voltage to all those capacitors have the input voltage. Huh? All of them. Number one. Number two, what we have done is flipped all the switches to the other side. Actually, when you open this, the amplifier doesn't do anything anymore. Meaning that indeed, when all of them are now connected to ground, then that input voltage which was on all those capacitances are going to be, since this is now 0, that means the other side will go to minus V in. This line goes to minus V in. And now we are ready for the charge redistribution for the successive approximation. That's going to be the next step. But I hope you see that when all the switches come from right, all of them, we go to left and we open the amplifier. And this is switched to the reference, that we have now the input voltage on all of them. And now the work has to start. Here we go. I'm going to switch only one to the other side. Here it is. You see? Only the left one. Why? Because I'm going to compare, as I did in the successive approximation, I'm going to compare my input voltage to half the reference. And then to half plus 1 half, to 1/4, and 1/8, and 1/16, 16, and so on. So I'm going to use those switches to approximate the input voltage by means of a reference voltage divided by 2, by 4, by 8, and so on. So indeed, when I go to this, I see that now the reference voltage is going to be applied to this point here. All the other ones are connected to ground. So we make a capacitive divider, and that goes to the input of this amplifier. So we had originally the minus input voltage, and now we add the plus the reference voltage, because the plus the reference voltage, we have exactly the same capacitance here as 8 plus 4 plus 2 plus 1 plus 1 is also 16. So that means that we have now half the reference voltage. If this switch is connected to the left, we add half the reference voltage. And this amplifier or comparator is going to figure out, are we now positive or negative? Where are we with this value with respect to the previous one? And then afterwards we have to add this one to figure out this is larger or smaller, and then this one, and then this one, and that's how you do the successive approximation. This is called the bit cycling. That means that we are going to try to approximate the input voltage by means of reference voltage divided by 2, and 4, and 8, and 16, and 32, and so on and so on. And that's how it works. It's a very simple setup. Nothing consumes power except for the comparator. We're going to make that dynamic later on, and we need a bunch of capacitances, and you know how to do that. And how much time does it take? For 10 bits, 10 cycles. Okay? So that works well. Very little has to be said more about this. Shall I show you some realizations? You will always see in all those realizations a comparator, of course, which is going to use a number of matched capacitances, 1, 1, and then 2, all the way to 128. 128 is 8-bit, isn't it? 2 to the 8 is 128. That's the biggest capacitance, that's the smallest one. Everything depends on how small that capacitance is for two things. First of all, we will have noise coming in, but secondly, the matching. Normally, the larger the capacitance, the easier it is to match. If it does not match well, we will have to do something about it, and that's it. So indeed, this is an old one. You see that indeed an input voltage is approximated by fractions of the reference voltage. Here we have a switch that works as a kind of sample and hold, and here is a comparator, and that's it. You see that the unit capacity is still quite large at that time, and that's the thing that has changed. Today we are at 1. A number of years ago, they were still using 12 femtofarad rather than 1. And the total amount of capacitance, you can easily figure that out. 128, this one, is 3 picofarad. Okay? This is an old realization, not too bad, but it's an old one. And when you look at that realization, you see that for one of the better numbers in here, we have an effective number on bits corresponding for 5 kilohertz input. This is already for portable applications. For 7-bit only, it is made for 8-bit, but when you do the measurements, you lose a bit everywhere. Running only on 1 volt. We find that indeed for 7-bit, 5 kilohertz or 4.6 kilohertz, only consuming 3 microwatt, you get something like 2.6 picojoule per conversion step, which is not too bad. Nowadays we are a factor of 1,000 less, but this is 6 years ago. This is old. In 0.25 micron CMOS. A more recent one is this one here, where again you see that there are some disadvantages and advantages. It's easier not to go with your input voltage to all the switches. There's too much capacitance. It's nicer to go to a sample and hold. But you see we have exactly the same ingredients. We have a comparator here. Okay, a comparator, you see the capacitance bank, which is switched in and out all the time. Unit capacitance is very similar. So we would expect a similar figure of merit of so many femtojoules per conversion step. This is 9-bit. The total capacitance is a little bit larger because this is a little bit larger. And when you look at the numbers, you're right, indeed. Well, it depends on which ones you take. If you would like to work on the supply voltage, which is a bit smaller, at 0.6 volt, we get something like 1000 here. Meaning that indeed, when you look at the effective number of bits, which is extracted from the number of, here it is, for 0.6 volt, which is something like 46.5 dB, 46.5 dB, going down already at the supply voltage of 0.6 volt. For 17 kilohertz, it consumes 3.1 microwatt. This corresponds to half a picojoule per conversion step. Half a picojoule is a lot less than a 2.5. So this is better. There are some advantages simply in that the input voltage is applied through a sample and hold, the power of which is included. We have slightly larger capacitances, which allow you to go to a little bit further in number of bits. But as you can see from the 9-bit, there is only about 7.4 bit left. It's designed for 9-bit, but the effective number of bits given by this kind of a measurement depends on the supply voltage, but I've taken the highest value here. I could have taken, of course, this value for 0.4 volt supply voltage or 0.5 volt supply voltage. You see that here the effective number of bits is going to be smaller. At 0.5, we are a little bit less. We are here somewhere. Okay. So be careful with titles of papers on this. It's the effective number of bits you have to have for a certain supply voltage. And that says it all. Half a picojoule per conversion step. Is that the state of the art? No. State of the art is found on this characteristic. It's the same as what I've shown before. Let me show you which one this is here. You see, this is very low. This is a power divided by frequency of 1 picojoule for only 40 dB signal to noise and distortion ratio. This is on the line of 10 femtojoule per conversion step. Which one is that? This one is this. This one from here. Not bad. Yes. Actually, it hardly shows the capacitance. It only says something about the comparator. The comparator is, of course, is dynamic. It's only switched in when you need it. And it doesn't use the fixed running clock. It's asynchronous. All tricks which are used to reduce the power consumption. Asynchronous clock and very little power consumption because it's dynamic in the comparator. And not a lot of detail here, but when you look at the numbers that you can achieve, this is already at 10 femtojoule per conversion step, which is very nice, of course, 19 nanometer CMOS. So no running clock, dynamic comparator, and a bunch of capacitances. And the most recent one, I'll show you in just a moment, the comparator used in there I have discussed when I talked about comparators. It's dynamic. You see that indeed there is a switch connected to the current source transistor for the differential pair, followed by a latch. I've talked about comparators. This one was included there. The main thing to see is that it's a single stage. Of course, there is a latch in there, and the current source is switched in and out depending on the clock. And there is some more. I'm not going to repeat what I've said before. We need some different capacitances to cancel the offset of the input pair. Otherwise, you can never go to very high number of bits because there is an offset which limits the comparison that can be realized by such a comparator. So this is all included, and this is why you can get to something like 10 femtojoule, which comes out very nicely when you compare with all the other A to D converters. The number of bits, the number of dBs is not very high, but the power consumption is very small. It's 10 femtojoule per conversion step. Okay? Beautiful. And another one which goes in the same direction. Impossible for me to say which point do you prefer. Do you prefer this point here, where you only need 1 picojoule to do it, but you only get 40 dB? Won't you rather prefer a little bit more power and go to 55 dB? That depends on the application, of course. Both of them are very close to this line here, which corresponds to 10 femtojoule per conversion step. So they are nearly as good. And they use very similar tricks. You see again all the capacitances here, and the comparator, and some logic. Never high frequencies. I'll show you the highest frequency in just a moment. 10-bit, that depends on how well you can match those capacitances. Very little power, going to 4.4 femtojoule per conversion. That's even better than 10. That's amazing as performance. And when you look at the comparator, the main thing that you see is that you don't see a lot. It's just a differential pair, but it's clocked, and that's why it doesn't take a lot of power, and then just a latch, and that's it, running on 65 nanometer CMOS. So this was not in the journal, but it was on the ISCCC a few years ago. So it's always the same kind of ingredients, matched capacitances, a dynamic comparator, and that's it. And also one from here, I mentioned that because this number is quite large, quite nice. If you need more detail on any of those, look in the Journal of Solid State Circuits. Most of them are in there. Again, we have here a number of capacitances, a track and hold to keep the voltage constant during the time that you do the successive approximation, the bunch of capacitances, and then a comparator, and of course the register that says whether I have to go lower or higher with my next fraction of the reference voltage. So when you look at those, you see that indeed for low voltages like 1 volt, how do you make switches? Well, some information on bootstrapped switches. Those are the switches to store the differential input voltage on those two capacitances, and then only you can get into the register. The comparator is very similar. It's different but very similar. Again, there is DC current, but it's switched. It's a dynamic comparator, which is essential to have very low power consumption. Also, this comparator I have discussed when I talked about comparators. So, and what is the most recent one? This one here, given last week Thursday in San Francisco, the ISACC. What they try to do is that they have given up matching. Why is that? Because the minimum capacitance used in there, you see the minimum capacitance, I've added that yesterday, you may not have that, is 1.6 femtofarad. This is not the champion. The paper after that was 1 femtofarad as a unit capacitance. If you do that, you don't have matching anymore. So the only way to get out of this is to try to figure out something to correct for things. That's not the correction which is in there. There's no correction for the mismatch of the capacitances, meaning that indeed you are able to match capacitances of the order of magnitude of a femtofarad. Beautiful. But everything else is included. They try to go a bit faster. What happens when you go faster? When you go faster, you always have to wait until the capacitors are charged or discharged. Remember the switch cap story. So that means that there is a settling time in there. You need 6-7 time constants before you reach the final voltage on your capacitance. So that means that if you try to go faster, you don't wait that long. So what they try to do is to introduce a correction for two-shot settling times, some other noise phenomena, especially one of ref noise, and metastability of the comparator. So what they do, rather than to go binary, and you see this as an attempt to explain that the input voltage is compared to the reference voltage divided by 2, divided by 4, divided by 8, etc., etc. Non-binary is not actually used in there. But what they do is they shift the range for the comparison by one least significant bit. Rather than to use between 2 and 4, they shift it to 3 and 5, and they do another comparison. And if the result after a level shift over a least significant bit is the same, that means that you are within the least significant bit. Otherwise, there is an error, and you correct for it in a digital way. So that's actually a kind of digital correction based on the fact that you shift your comparison range over a least significant bit. And if you do that, that's how you catch errors as a result of two-shot settling times and some other errors. Works fine. Yeah. You see the same ingredients. It doesn't show all the digital stuff to keep track of all this, but you see all those capacitances again. Okay. You see the comparator is fully differential, of course, and this is where all the logic is. And you see that indeed, of the 13 bits left, there is only about 10 bits left. But when you look at the numbers used, 1.6 femtofarad, and you do that up to real high speed, the correction is made to correct for lack of settling time. You don't have time enough to settle. It's a correction to do that. Well, there is still a lot of bits left. 9.5 of the original 13, 9.5 left. And if you do that at 1.2 volt, it's something like 65 nanometer. There is 15.5 femtojoule per conversion, which is beautiful. 15.5 femtojoule for conversion. This is beautiful because all the previous ones never made it that high in frequency. This is a low frequency technique based on matching. And when you push for high frequency, you introduce errors which ruin your effective number of bits. But this is the state of the art today. And the power is small because it's a dynamic comparator, of course. You see that there is kind of an equilibrium between the analog power and the digital power and the DAC used in there. It's all about a third of 1 milliwatt. That's about the best you can do today. Small area because it's all about small capacitances. The total capacitance is less than 2 picofarad. So it's a small 0.026 square millimeter. Wow. So this is good. Beautiful. That's what you can do today with successive approximation. But we have some other things to talk about, of course. algorithmic and flash and so on. Let me do a few more, since we started a bit late. What is an algorithmic one? Well, what we did before was try to approximate the input voltage by adding or subtracting the next fraction of the reference voltage. So you compare the input voltage with the reference divided by 2. You add subtract reference divided by 4. Add subtract reference divided by 8 by 16. So we have that factor of 2 coming in there as the result of reference voltages created by a binary set of capacitances. A algorithmic or cyclic A to D converter is going to do something else but very similar. What it's going to do is, first of all, remember the input voltage and do the comparison indeed, do the comparison with the reference voltage, and the difference is multiplied by 2. So this time what we are going to do is we are going to have a comparison and we are going to add the same reference voltage all the time. That difference is going to add or subtract a reference voltage, and the difference is multiplied by 2. So we can use the same feedback loop rather than to have to compare with half the reference, a fourth of the reference, an eighth of the reference. We compare it with the same reference, but the difference, the residue, or whatever you would call it, is multiplied by 2, and then we can use the same feedback loop. So if we do that for 10-bit, we have to do that 10 times. Okay? So that means that we have to the accuracy now, since we use the same comparator again and again and again. We don't have to have accuracy in the creation of the reference voltage or in the creation of a capacitance bank, which has capacitance in ratio 1, 2, 4, 8, 16, and so on, okay? Which is actually a result of matching of capacitances, which we know how to do. Now we don't have that anymore. We have a fixed reference, but now we need an amplifier by 2. That's the difference. Can you make an amplifier with gain of 2? Sure. You take 2 capacitances, which are equal, and they have an amplifier with a gain of 2. Of course, the capacitors have to match with the same kind of matching accuracy as for the capacitance bank we had before. So it's not better in terms of matching than the previous one. It's different. So now, of course, we have an amplifier times 2, which is going to be a result of 2 capacitances. And parasitic capacitance is going to give you an error on that, in very much the same way as a parasitic capacitance was ruining your accuracy or resolution of your capacitance bank. And it takes the same time. So it's very similar. How does it work? In the same way. You can see that indeed the input voltage is switched in first. And we see whether this input voltage is larger or smaller than the reference voltage. And then we switch in, this is actually the DAC, then we switch in that voltage, the reference voltage, we add it or subtract, and the difference is going to be held also because it's a different timing, divide by 2, and then this is going to come back in this loop here. So algorithmic or cyclic A to D converters are not used very much. It's the same thing as the previous one. Okay? And we would rather go to a pipeline where rather than to do that with the same feedback loop, we're going to have a number of loops, one after the other. So this is not used very much. The flash A to D converter is a very different one. It's the highest speed one because we do everything in parallel. The previous ones did 1 bit at a time, isn't it? Success approximation. The slowest one was the first one, the integrating one. The integrating one took a lot of time because for 10-bit that was 1,000 steps, endless. Whereas the success approximation, 10 steps, that's reasonable. The previous one too. This one takes 1 step. It's the highest speed one. Of course, it takes a lot of real estate, amplifiers. Because if I take a reference and I scale down the reference by means of resistances or later on capacitances or later on offsets of amplifiers, but let's take resistances first, then we see that if this is 1 volt, this is 0.9 volt, 0.8, 0.7, and so on and so on. We scale that down to the lower value. Now the input voltage is applied to all those comparators, figuring out, is my input voltage now larger or smaller than the reference voltage, the scaled reference voltage? If my scaled reference voltage is here somewhere, then all of them here give a 1. We have a 1 there, and we have a 1 there, and we have 1 there. and all the other ones above those is going to give you a 0 and a 0 and a 0. So we see we get kind of a thermometer code indicating simply where my input voltage is with respect to the scaled reference voltage. So we need an encoder to convert that thermometer code, all the ones below and all the zeros above, to something which is a real digital code. Okay? So we need an encoder which has got to be fast, but there's a digital logic, of course, and we need all those here. And the problem with this is that, well, first of all, it's beautiful, it's fast. Only one step, you can't beat that. And indeed, if this is real fast, you get a digital output real fast. But the problem is that for 3-bit, for example, I need to be able to resolve, 3-bit is 8. That means that I have to have 8 of those comparators. So that means that if I go to 4-bit, I need 16 comparators. And then I go to, for example, 6-bit, then I need already 64, 128, depending on how much is 3-bit. 3-bit is 8, and then 16, and then we have 32, and then we have 64 of those comparators. 64 comparators, that's going to take a lot of power, of course. So we will need a whole bunch of derivatives of this flash converter in order to save on comparators. And I'll give you a number of techniques. Save on comparators to reduce the power consumption. But this is the fastest one. Nevertheless, it has been done up to 6-bit, for example. It's not that many comparators, huh? Going to very high speed. The highest speed ones are flash converters today. Well, the competition, I'll show you later on, is interleaved pipelines, where I take a whole 120 pipelines in parallel to make it fast. That's the competition, huh? But they are, in principle, for single step, are the fastest ones. So when you look at that, you see that indeed, when you look at the plot already of some time ago, we see that today people are trying to make a few gigasamples per second with flash A to D converters. That's today, huh? With 6-bit. 6-bit is still a reasonable number of comparators. In competition with, as I've said, with pipelines, which we're going to discuss, but that's what they try to do today with just flash. 8-bit is too many comparators. This has been discontinued. Huh? Nobody does that anymore. Too many comparators. Or doing some variations on the theme of the flash A to D converter. The first variation on the theme, and then I'm going to stop it. It's coffee time. Is, can't I do something about that number of comparators? Yes, let's do it in 2 steps. Whoops. We give up the most important advantage of a flash converter. You could do it in 1 step, but 2 steps is maybe not that bad. It's only a factor of 2 worse. And we have many less comparators. You save a lot of power. Huh? So you see again that exchange of resolution versus power consumption. They're going to give you comparable picojoule per conversion. Huh? But if you do it in 2 steps, how does it work? Well, I take a 4-bit A to D converter, which is not too bad. 4-bit means we have 4 times 8, only 16. 16, yes, 16 comparators. And that 4-bit A to D converter, we allow it to follow by a 4-bit DAC. So what we get out of it is an analog signal with 4-bit resolution. 4-bit resolution, fairly crude, 4-bit is not much. Huh? And then we compare the original signal with that crude analog signal here. So the difference between those two is all the detail with respect to a 4-bit approximation. And the detail is small, of course, because if you multiply that by 16, then we have a full scale again. And then we could do the same thing. This one is exactly the same as this one. We make 2 equal 4-bit A to D converters, flash A to D converters. All of them, both of them have 16 comparators, 16 comparators. That means that now we have 4 plus 4, we have 8-bit resolution with only 16 plus 16 is 32 comparators. If we did that directly, we needed 256, and now we only have 32 comparators. Isn't that big savings? Yes. And it's still 8-bit, same resolution. Of course, we can't forget that there is a 4-bit DAC in there, but a 4-bit DAC is not that big, it's easy to do. Okay? So that means that the 2-step of sub-ranging flash A to D converter is savings in comparators, simply because now rather than to need 256, which we would need for a straight or single step 8-bit flash A to D converter. Now we only need 32. We need a DAC, but the main catch is, of course, that factor of 16, which was the difference between what we had after the 4-bit conversion and what we had originally. We need an accurate 16-bit amplifier, and that's a problem too. So it's not that easy. 16-bit does have the accuracy for 8-bit, which is not that bad. An 8-bit accurate amplifier is not that difficult to do. Okay, so this is used. That savings is too convincing not to use that. And 16 with 8-bit accuracy is fairly easy to do, and a 4-bit DAC too. Okay, so this is a 2-step A to D converter. If you would like to go further, we could do some trimming on this, for example, if this can't be done. For speed, you would like to go to 45 nanometer, for example, for real high speed, and then you would have to do some trimming or digital correction and things like that. And it takes 2 steps, of course, and even more, because you don't do it in 1 step. So this is a valuable alternative. So shall I show you a fairly recent flash A to D converter doing that with beautiful performance? It's not a 4 gigahertz one, no, it's a low frequency one. Oh, yeah, really ought to stop it. It's over there. Yes, in the same corner again. Yes. Here it is. All the tricks, it's a flash A to D converter, but rather than to do this, what is done? Rather than to do that, rather than to have references here, the references are in there. That means that the differential pair, which is doing the comparison, has an asymmetry in the input pair. It's as a reference voltage is put in series with the differential input pair. If I made the differential input pair asymmetrical, I create a large offset, and the offset is the reference. So rather than to use those resistors, I use the same comparator all the time, but each of them has a different offset voltage, and as a result, they give you 1 or a 0, depending on where the input is with respect to the offsetted input of the differential pair. This is what this is doing. And all the comparators are dynamic, of course. All the comparators are dynamic, of course. And the amplifier, and you see how many of those do we have? You see clock comparators. How many do we have of those now? Well, 128 I see. So this corresponds to so many bits. Huh? Let's see how much is coming out of there. There is no biasing anywhere. All the comparators used in there are just differential pairs. I'll show you just differential pairs with different transistors, which are clocked. So we don't use them all the time. So the currents are small. And then afterwards, to make it sure, because the gain of such a comparator is no good, there is digital calibration afterwards. Digital calibration, all dynamic, are the tricks to go to low power and to high accuracy. See, this was not too long ago. This ended up in the journal fairly recently. That's the kind of performance you can get. Huh? And when I look at the comparator, you see this is nothing else than a clocked differential pair, where all transistors have different sizes in order to create an offset voltage, which is used as the reference voltage. So the input voltage is going to give you 1s and 0s at different values, depending on the relative size of the 2 transistors of those pairs here. There are a number of them in series, a number of them in parallel, and all the configuration is different for each of those comparators. Beautiful. How much can you get with this? Oh, less than 1 picojoule per conversion, of course. Look at this. Versus supply voltage. The optimum is here, of course. 1/10 of a picojoule per conversion step. And if you go to something like 0.2 volt supply voltage, yeah, you can go low with just a differential pair. Eh? Of course, you lose a bit performance. This is the best. You lose a bit over there. Okay? And you see that when you go higher and higher in current, of course, the sampling frequency goes high. From very low at 0.2 volt to much higher, because you consume much more current, of course. Then you have something like 70 megasamples, which is not bad. So less than, but then at that point, at the highest frequency, you go back to something like 1 picojoule per conversion step. The minimum is here. This value is about the same as over there. But that's what you can do with flash. This is flash. Let's have a break first before I will continue. I will continue again in 20 minutes, if that's okay with you. So, ladies and gentlemen, I'm back in the air. We have some other techniques to cut down on number of comparators in flash A to D converters. Those techniques are interpolating, folding, interpolating or averaging, folding, the many names. So let's have a look at that in a bit more detail. Those are used. And then the pipelines, of course, we have to discuss pipelines and then some comparison at the end. Another comparison, as you can see, in A to D converters is all a question of how much power do you need to get that frequency converted with a certain resolution. That's why I spend so much time on comparison. First, interpolating. Well, we try to save. I'm going to talk again about that flash A to D converter, remember? Shall I remember this one here, the original one? Here it is. We would like to throw out some of those fellows here. But how do you do that? All of them consuming power, especially if you're interested in speed. We can try to make them dynamic, but how can we throw out some of them? Well, interpolating is one technique and folding is the other one. Here we are. You see, what we try to do is to give the impression to those comparators, or shall I call them latches, same thing. As a result of an input voltage, you latch to a 1 or a 0, that's what it does. We try to throw out some of them. Well, this one here is thrown out. We have been able to leave out. How is that? Well, by averaging the output voltages, or by interpolating between the output voltages of preamplifiers. And those preamplifiers are amplifiers which amplify 5, 6, 7, 8 times, which saturate. So let's have a look at one amplifier first. One amplifier first. This is input voltage and this is the reference voltage. What is that amplifier going to do? It works like a comparator with gain. It's going to do this. This is the transfer characteristic of this first amplifier here. Here is a transfer characteristic. You will recognize immediately when the input voltage goes higher, the output voltage goes lower, as in most amplifiers, isn't it? Oops, I should follow the line, sorry. Let me try to follow this line here a bit more closely. I have a bit more spatial noise in my fingers. Oops, that's the time difference. Oop. Yeah, that's a lot better, isn't it? You see what the amplifier does? It's saturating, it stops somewhere, and of course it's going to bend a little bit. And it goes like this. And it works like a comparator in the sense that when this voltage is higher or lower than the reference voltage which is here, is going to give you a 1 or a 0 in that latch. So that's what it is. Now, if I take that second one, which is over there, and I'm not going to draw that, but this one has this characteristic, this characteristic, which is going to give you a comparison around reference voltage 2. Now, if I take two resistors here, what is that latch going to think? That latch is going to think that there is another amplifier right in between. Because indeed, for this latch here, it looks like I have this averaging characteristic between the two previous ones. And I have created the impression that there is a reference voltage exactly halfway between the two other reference voltages. But there is no amplifier there. So actually interpolating is adding resistances at the outputs such that the latches work with a reference voltage which is created between the other reference voltages. It is an interpolated reference voltage which acts on this latch here. So interpolation saves amplifiers. Now you can do that, of course. Let me show you a real example. This was just a sketch for a 4-bit realization. It's a bit smaller, but I hope you can see it. You see immediately that we have here that amplifier and another amplifier and another amplifier. Again, the reference voltage is scaled by means of the resistances. We have 1 volt there, 0.75 volt here, 0.5 volt there, 0.25. Scale the reference voltage. And those amplifiers are going to figure out, is this input voltage lower or higher than this one, with the saturation amplifying characteristic. So that means that indeed this latch is going to figure out, is it larger or smaller than 1 volt. For this one, Is it larger or smaller than 0.75 volt? But between the 1 volt and the 0.7, we need to put some resistances here to interpolate between the 1 and the 0.75, and as a result, those latches are going to do a comparison of the input voltage with respect to references which are between 1 and 0.75 volt. You see we have 4-bit interpolation here. Works fine. If I just take one of them to show you that in a little bit more detail, what are the advantages? Of course, 3 out of 4 amplifiers are left out. And on top of that, something I forgot to mention, indeed that input voltage here sees in parallel all those blocks. So if you have 256 of those comparators, you have 256 times the input capacitance. So a flash A to D converter has a huge input capacitance, quite often a buffer to be able to drive that, and that buffer at the highest speed takes an enormous amount of power. Here the input capacitance is also divided, because 3 out of 4 are left out, so the input capacitance is smaller. If I just take the bottom one to show you that in a bit more detail, so this is a copy of the previous slide just to show you what happens between V2 and V1, for example. The transfer characteristic corresponding to the 0.25 and the 0.5 are here. Those are the two extremities. This is the one corresponding to the transfer characteristic for the amplifier doing comparison around 0.5 volt. And this is the one around 0.25. And you see that the ones in between are doing exactly comparison of the voltage with respect to the intermediate references there and there and there. You see? Works fine. This is a gain of 10, for example, easy to do with the GM over GM ratio. That's the kind of amplifier you make. I don't have a circuit here, doesn't matter. You average out some other effects, for example, some offsets are also averaged out. Of course, you have some problems if you do that real fast, because this is at the output of an amplifier, that goes real fast here. But of course, this one is going to be a bit slower. You have a series of resistance there. So with the high speed realizations, we're going to put in some resistances here as well in order to equalize the speeds, and the smaller resistor there, lower resistor here, a smaller resistor there, and a much larger resistor there to equalize speeds towards those several latches. And there are little tricks to make it a bit faster and so on and so on. Okay, that's interpolation, saves on those preamplifiers. Do you have to do that with voltage or with current? Both exist. I know how to make a voltage halfway those two voltages. You average or interpolate by means of resistances. This is going to be V in plus V2 divided by 2. That's what we just did. And I'm not going to calculate the other ones, but that's what we just did. Of course, you can also do that with currents. As you know, currents can give you some advantages. Too many advantages are attributed to currents, but whatever. So if I take just here a current source rather than a voltage source, this is now an input current rather than an input voltage. This is another input current. How can you interpolate? Very easy. You just take a current mirror 2 to 1 and 2 to 1. So this current is going to be the half sum of the two currents. Okay. So whether you do the interpolation by means of voltages or currents is not going to make a big difference. It is different, a little bit more complicated here. You see this is now interpolation by 3 rather than by 2 just before. You see that now we have ratios 933, and those output currents here are going to be combinations of the two input currents. As you can see, 2/3 there, 2/3 there, 1/3, 1/3 there. Easy to do. Current mirrors are high speed circuits. Work fine. Okay. So this is the kind of circuits, and if you look at, for example, a current interpolator, of course we still have to convert voltage into current and then to play all those tricks, and then play all those tricks. This has been done, high speed A to D conversion, sure, it's flash, but we use interpolation to cut down on the number of comparators or amplifiers. And the other amplifiers used in there are of this type, for example, where you do compensation of the output impedance. I have a high speed amplifier. Okay, those are the amplifiers used in there. As long as the gains are more or less similar. The gain itself is not all that important. It's the crossing point that's important. So the actual slope is not all that important. as long as the crossing point is important. And this depends on offset, not on the actual gain. And offset has to do with symmetry. Symmetry, symmetry everywhere. I'll talk about symmetry a lot in 2 weeks when I talk about DAX. This is all about symmetry. So this is all about symmetry on top and at the bottom. So this is a kind of amplifier used for this. Now, of course, how many of those are you going to do? Well, it's all a question of capacitance and speed. So this tries to say, well, how many transistors, when I take the previous circuit here, for example, how many transistors can you connect on the same line to do current interpolation? The more transistors you put in parallel for more interpolation, the larger the capacitance is going to be and the slower it's going to be. But then you could do more interpolation, then you need less stages. So the power consumption goes down if you do more interpolation, but the speed is going to go down too. Because the capacitance increases because you put more transistors in parallel. So you can easily figure out, when you do a design, this kind of a compromise, when you have the number of transistors connected together means more interpolation. More interpolation, that means that the speed is going to go down, this is speed. And the capacitance is going to go up, of course, because you have more transistors in parallel. So this may determine how many of those interpolation stages you would like to put in parallel. The other trick is folding. Interpolation. The other trick is, why do we need tricks? Because a flash A to D converter, which is the fastest, needs too many comparators. And all those comparators, 256 comparators, is going to kill the performance because it takes too much power. One trick is interpolation, the other one is folding, and of course, after that, we'll combine those two. And those are the ones that you use instead of the pure flash A to D converter. What is folding? You fold the input signal over a smaller range. This is an important graph. It says what is the folded signal with respect to the input signal. And it goes up and down. It is folded. Folded is a term used for cascodes too and some other things. But here it's indeed folded when I look at the output signal. And I'm talking about this block here. What's coming out of there is a folded signal, and what's going in there is a non-folded signal, the input signal. And the input signal has a wide range. And look at this. This goes from 0 to something real large. Shall I call that a volt or something? Voila, here we go. And you see it's folded because it goes up and down, and up and down, and up and down, and up and down. This is four times folded. Meaning that now, if we are going to make an A to D converter, the A to D converter has to work over a much smaller range. You see? Actually, the A to D converter has to work over, not over 1 volt, but actually it has to work only over 1/8. For this example, over 1/8, because I have 1, 2, 3, 4, 5, 6, 7, 8. That means that I have to make a flash A to D converter, not over 1 volt, requiring 256 comparators. I only have to do that over 1/8, and as a result, I only need 256 divided by 8, which is 32. So what I do here is I fold my input signal to limit the range over which the flash A to D converter has to work. And as a result, I need much less comparators, of course. But there is one thing I have to remember. I have to remember in which part I'm working, whether it is in this one, or in that 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 one. How many times did I say that? 8 times. So I need a coarse A to D converter to figure out whether I'm working in region 1 or in region 2. I'm going to use normal numbers. I'm not going to talk in terms of 000 and 001. No. It's 1, 2, 3, but those are normally digital numbers, of course. So if I take a coarse A to D converter, here it is, directly on the input signal, yes, to figure out in which of the 8 regions that I'm going to be, and in parallel, I'm going to do a fine A to D converter with only 32 comparators. Then I have a flash A to D converter which saves the number of comparators. So I need a coarse ADC, I need a fine ADC, which is going to be a number of comparators, and I need a folding circuit, which is going to fold my input circuit, which normally would go all the way up, all the way up to over there, but I fold it, so that I can do this kind of conversion. Works beautifully. Yeah, here is one. Yeah, It's a bit complicated maybe, but I'm going to show it how it works. Yeah, it's 4 bits, so you can see it. If you go further, it's too cramped. Huh? You see the input signal here? Here is the cause. Here is the cause, 2-bit. Yeah, 4 corresponds to 2-bit. Here is the cause, 2-bit flash A to D converter, which is going to indicate in which of those regions I am. Okay, and now here are the folding blocks. Folding blocks with different references. What is coming out of this one here for the input signal is this. You see the folding? It's not as sharp as before because this is done with real transistors now. It's never that sharp. You see the 4 regions, 1, 2, 3, 4. Okay, and the next folding block is shifted over some voltage because you see this is going to start a little bit earlier. This is 1, 2, 3, 4. The folded signal on this one is this one. The folded signal on this one is this one here. And now how does it work? Well, shall I show you how it works? Now if I take an input voltage and allow it to slide from 0 to the input voltage, the final input voltage, we have to figure out with those 4 inputs what kind of a digital code are we going to get. In order to do this, I have to, oops, let me take that out and a bit bigger and a bit smaller maybe. Oops, I have to change my, that is not going to work. Oh, whoa. I went too far. Yeah, here we go. I have my sliding rule on the right, but my scale is so different here. Yeah, I can do that, I think. This is a very low resolution. Oh, I need a bit more on there. Let's see how can I do that. Making a bit smaller maybe. I'll take the first 2 ones. The 3 ones. If I take my input voltage here, you see, for a small input voltage, here this is below the threshold voltage, so this is going to be 0, 0, 0, and the other one 0, 2. But now if I move to the right, which one is going to switch on first? I go, for example, that far. Now I see that here on the bottom one, let me show you the bottom one. I have already 1, 1, 1, and a 0 on top. So for each of those, which is hard to do with this kind of a scale, I have 1, 1, 1, 0. This is already this one here. So when I slide with my input rule from left to right, because there is a shift in each of those curves with respect to the other ones, I get a different digital code out. And when I'm over here, then it's the other way around. Here I go from 0, 0, 0 to 0, 0, 1, and then to 0, 0, 1, 1, 0, 0, and so on, until they become all 1, but here it's the other way around. Because here they are all 1, 1, 1, 1, 1, and then on the bottom end I have already a 0, so this 0 comes first, and then 2 zeros, 3 zeros, and then 4 zeros. So when I'm sliding over those, I go from 4 zeros to 4 ones, and then it's inverted in the next region here, and then it goes up again, and then again. So the only thing I have to remember with my most significant bits is that am I in here in this region, or in this one, or this one, or this one? And then the actual A to D conversion is simply a result of going up with my input voltage. And as a result of the folded signal, I get the right zeros and the ones. Let's see where I go back to this. Now I can't change this here. So this going up with the input voltage shows that indeed I get the right digital code coming out. And if I know the most significant bits here, I know this is a 4-bit folding ADC. Works fine. The question is, of course, how do I generate a curve like this out of an input voltage? How do I do the folding? The rest is simple. We talk again about latches, some logic, encoding, and so on and so on. So this is a folding circuit. Again, it's a differential pair. We have known a differential pair for, I don't know how many years, I have known the differential pair for a very long time. Huh? This is simply connecting differential pairs with different reference voltages in order to set, you see that with this reference voltage here is this one, meaning that indeed what is the characteristic of a differential pair? It is a S characteristic like this. One resistor is on or the other one around the reference voltage. Here it is the reference voltage over there. And of course, if I take that in parallel with another one with a different reference voltage, and I combine the outputs in the right way, then it goes back again. So this is the characteristic of the second differential pair, connected in opposite phase. And then we have two more, and then if I take the right connection of the differential pair, this signal has a behavior like that as a result of the input voltage connected to all four of them in parallel, high input capacitance, there we go again, okay, with respect to four different reference voltages, and there we are. So folding is easy to do. It has a large input capacitance, but it's easy to do. Okay? And now what we are going to do, and that's a real realization, is a combination of folding and averaging, of course, because you see now that this is not only folding because we have the most significant bits generated by this block on the side. This is a folding block, and also the outputs are averaged. So this folding block is saved. So this is a way to save both on comparators and amplifiers. As the result of this resistance we have interpolation, and as a result of this we have folding. And as a result the number of comparators plus amplifiers is fairly limited for high speed for the same principle as a flash A to D converter. So this is what people realize nowadays. It was done already a long time ago. That's interpolation and folding. I could have shown you some amplifiers doing this, and show you again some femtofarads, some femtojoule per conversion steps. I leave that pleasure to you to fill in all the dots. This afternoon you go to the website of Boris Merman and you try it out yourself. It's great fun. But I have to talk about pipelines. A pipeline is a pipeline, meaning that you have several blocks one after the other. And I've picked this from somewhere, a thesis, showing that indeed everything is fully differential. Of course, the analog input is buffered, and then you have several stages, one after the other. Usually the last one is just a flash one. But a flash one can never get you 10, 12 bit. Pipelines are more ambitious. They want to go to 10, 12, and even more bits. Okay? So the last one is always going to be, you see 5-bit, a 5-bit A to D converter flash, easy to do, not that many comparators. And here we have a first stage, which actually is going to try to do a 3-bit conversion. I'll show you how this is done. We are not going to use the 3 bits. We only use the first 2 ones because the third one is lousy, doesn't work well. So we use the redundancy in there. It's meant to be 3-bit, but we only use 2. Same thing here. It's a pipeline with equal stages, stage number 1, stage number 2, stage number 3, stage number 4, and you see how much variability you can have. I could have taken 5 stages and here less bits, or more bits there and only 3 stages. So there are many different pipelines, but all of them have at least some stages. And sometimes you use 1 bit, sometimes 1.5 bits, sometimes 2 bits, sometimes 3 bits. But all of them are going to do a conversion with a very, very limited number of bits, and then go to the equal stage, and the similar stage, and the similar stage. And usually, at the end, you have a flash A to D conversion. We have to keep track of all those bits, of course. And as you can see, actually this was meant, this is designed for 3 plus 3 plus 3 plus 3 plus 5, which I believe is 15. And what you're going to keep is only 2 and 2 and 2 and 2 and 2 plus 3, which I believe is, from the 5 there is only 3 left, is 11. Because, and this is called an 11-bit, but some people would call that a 15-bit pipeline. So what's in the name? Be careful with this. They go quite high up, 11-bit, 12-bit, up to 150 megasamples per second, so those are high-speed blocks. It's going to take power, of course, but we will see again that the power is used towards resolution and towards speed, to a reasonable number of femtojoules per conversion step. We use the redundancy because matching is never that good, so the last bit is not quite used because the range over which you have to do the conversion is too wide, so you limit the range, and then you can't have the full range, so you have less bits coming out. And it's always a flash at the end. The reference is used in each of those, but the reference goes through buffers, of course, because they draw a bit of power, and the power can't be taken from the reference, so you need buffers, which has to be included. One of the typical questions, are the buffers included or not? Things like that. So let's have a look how it works. Well, if I take one stage out of this, in general, I have to remember the input voltage, of course, because we're going to do one conversion after the other. Okay? And if I take an ADD converter and then followed by a DA converter, what's coming out is, of course, the difference between those two. So if this is 2 bits, then the error of the residue is going to be small. And when I compare that directly with what is left over here, then like in a cyclic A to D converter, but it's one after the other. Rather than use the same block again and again and again, I do it at one stage after the other stage. But it's very similar. If this were a single bit A to D converter, what does that mean, single bit? That depending on the analog voltage, this is the reference or not, or plus the reference or minus the reference. Converted to that, this is 1, 0, so that's going to give you the reference or not the reference. I have an actual example later on. And now if I compare with the input voltage, the difference of the analog voltage here subtracted from the original input voltage gives me half the reference, multiplied by 2 in this case, it's single bit, gives me the full range again. So that means that again, as for the cyclic A to D converter, I have to be able for a single bit realization to make an amplifier by 2. For a 2-bit realization, I have to be able to make an amplifier by 4. And for a 3-bit realization, I have to be able to make an amplifier by 8. And that limits the accuracy, because the rest, the reference comes usually from outside, the reference that I switch in, and that here is going to be a very simple comparator. In case of a single bit, for example, the amplifier limits the performance. So the solution is going to be there. And if I can't have actual multiplication by an accurate value, I have to do correction of that. So when I talk about digital correction, it's all working on this. And this is being used to improve both speed and resolution. So let's have a closer look to this. For example, for a single bit, this is the same as before. For a single bit one, that's how it looks like. I'm sure you recognize the ingredients in there, a sample and hold. I will show you at least one sample and hold. I have to show you once a sample and hold. But for frequencies up to a few hundred megahertz, this is not that difficult. The AD converter, what is that going to be for 1 bit? An AD converter for 1 bit is a comparator. Again, I've talked about comparators. Now the comparator gives you a digital signal. 1, 0, there it is, my first B, my first bit of my byte. And that is going to determine then which reference to switch in. A fraction of the reference is used all the time, either plus or minus. And that one has to be added or subtracted from this one here. Here it is. And now, of course, the signal here is going to be smaller, multiplied by 2. Now, if this signal is large, we will have an error. So we'll play some dirty tricks to have a smaller signal there. Okay? But if the signal is large, which is actually half the reference or a quarter of the reference, depending on which stage I am, I always have a multiplication by a factor of 2. So I can't stand linearity and noise and offset and those things, and that's the problem. So that has to be done for each particular. So you have as many stages as bits. This is too complicated. Now we are going to use the redundancy. Redundancy, what does that mean? We see that this is the output of this circuit here. When I look at this here, when I look at this, or shall I say over there, what do I get? Here it is. This is the input voltage. This is the input voltage. The input voltage is over there, also over here, input voltage. A reference voltage itself, or a fraction of the reference. And we see that if you subtract a reference voltage from the input voltage, it goes for 0 input voltage minus the reference is over there. This is for an input voltage a bit larger minus the reference is over there, and so on and so on and so on. I have a very wide range for that amplifier to cover, and that's a problem. Non-linearity and so on. So I'm going to do a bit of this, a half-bit kind of conversion of input towards the output. So that means that I'm going to use a redundancy. I do a conversion instead of 1 bit, 1.5 bit, or 2 bits or 3 bits, and I only use the coarse part of this pipeline stage. So that means that I lose part of that, but I don't care. So meaning that in the Oh, sorry. So when I look at the when I look at that stage before to show really what's going in is a continuous input range. That shows how this is actually working. This is the input range. That is going to be numbers, 0, 0, 0, 1, 1, 0, numbers. This here is actually the reference switched in. Those are actual voltages. Huh? I ought to make it green, but I'm a bit lazy at this moment. Huh? And then I do the subtraction of this reference voltages from the original. So if I subtract this from this, if I subtract this from this, what I'm going to get is what's blue. You see, that's the difference between the continuous input voltage and the reference voltage, which is switched in. And then the multiplier by 2 is going to give me again this. That's the multiplication by a factor of 2, and I have the same range as over there. Okay, so this is how it works. And again, this is the full range of this amplifier. We may want to take intermediate steps not to have the full range, which suffers from linearity, etc., etc. So the residue, this is called the residue, has to be multiplied by 2, and then you have exactly the same amplitude as in the beginning. And if I take that as a stage, and then the next one, and the next one, and the next one, that's how a pipeline is formed. So that works fine. So actually all this here, this is normally combined in one block. This is called a multiplying DAC, because DAC and multiplying by 2, maybe you can combine that in one little circuit. So this is called a multiplying DAC. Multiplying DAC. DA converter switching in a reference voltage and then multiplication by 2. How can this be done? Very simple circuit. Very simple circuit. Here it is. You see the DAC coming in, switching in a reference voltage. Here is the voltage from the previous stage. This voltage was the red one in that previous slide. And this is going to be generated. This is the multiplied by 2 blue one. Sorry, it's all black and white. This is the input voltage, and this is the output voltage. And how can you do the gain by 2 for a single bit pipeline stage? Well, with capacitance it's fairly easy to do. You see that in phase 1, for example. And then we are going to go to phase 2, but in phase 1. In phase 1, that voltage is simply applied to those two capacitances, which are in parallel, to ground. I don't use the amplifier, as you can see. The amplifier is not used. I just apply the voltage to the two capacitances. Everything else is open. Huh? Only phase 1 is closed, meaning that I apply my voltage to the two capacitances. And then what I'm going to do is switch the capacitances such that now I just have an amplifier with the capacitance in the feedback loop and the capacitance to the input. So since both capacitances are equal, I have 1 plus, because this goes to the positive side. It's 1 plus the ratio of the two capacitances is 2. And it's just the mismatch of the capacitance that determines how good the ratio 2 is going to be. Now I use the amplifier. So that means that if I have a pipeline set of stages, I need to use the amplifier now. So that means that in the previous one, I can use that amplifier in the next pipeline stage. I reuse the amplifier. Op-amp sharing has become a common technique to save power. Op-amp sharing. In this clock phi 1, I'm going to switch the amplifier to the next stage. And then I'm going to use it in this stage. And as a result, it's used all the time. That's one way to save power. And this is using the capacitance twice. It's using the capacitance in this to sample the input signal or to store the input signal, and it's used also to realize the gain. You see how simple this combination of DAC input and amplifier by 2 can be. Everybody is using that. And now depending on the size of the input capacitances, you can have excellent accuracy on that ratio of 2. Okay? That's a pipeline. Again, how large are you going to make the capacitance? How well can you match capacitances? The larger they are, the better you can match them. This is an old example, still talking about picofarads, huh? Because you can even match femtofarads. You see that indeed the error as the result of the capacitance mismatch goes down when you go to larger capacitances. And also the error, for example, the gain, the error on the gain is not that important. settling time is going to be a problem, of course. If you take larger and larger capacitors, don't forget we are talking switch cap stuff. Meaning that you have to wait long enough until you have the right voltage across all those capacitances. Otherwise, your factor of 2 is not going to be 2. So there is somewhere a compromise. There is somewhere a compromise. If you take the capacitance too large, you have to wait too long. And your maximum frequency is going to be too low. But if you make the capacitance too small, then the matching is no good. And then this is not right. And then you have an error. And then your pipeline, which was meant for 12-bit, is only giving you 8, 9-bit. Okay. So there is a compromise, as usual, between how much power you need for the capacitances over there. Some examples. Who are the champions in this? Well, did I pick one from the conference last week or from somewhat early? No, this is the conference last year. Okay. Well, those are good papers, so if you would like to read more about it, those are the ones to take. I've picked out the better ones I could find. There may be some of them from here, but not always. So, you see first stage 4-bit, another one, and then a number of them 1.5, simpler, 4 bits in the beginning, 1.5 there. This is a flash, only 3-bit. You only keep 5 bits from over there, 2 and 2. So altogether you get 16-bit. This is meant to be a 16-bit converter. Each of those are going to be the same thing. This is actually 4-bit, meaning that if you work with 16 levels corresponds to 4-bit, yes. Then you have to multiply by 8, only multiplication by 8 over limited range. You could do more actually. So there is a lot of redundancy in that type of circuitry. It's a flash A to D converter. This is the DAC, because as you know, you have to do the comparison between what you get through the ADC DAC and what you get directly. There is a sample and hold here, yes. And then you have to multiply the residue by the factor that you need according to this, and then do the same, and then something similar and similar and similar. Look at this. It's not bad, huh? 0.24 picojoule per conversion step is not too bad. Huh? There is a trick here to make it accurate. Otherwise, it won't work. So it's not just, there is also calibration. Huh? If you try that just like that, then you would never get the 16-bit coming out of this. So there is digital calibration in there. When you look at some of those blocks, they use the same blocks. Huh? The digital calibration is not shown when you look at one of those blocks. Huh? Because you see that in the 1.5 one, for example, you see exactly the same thing, a reference switched in the 2 equal capacitances, or different capacitances depending on how many bits you're handling. Huh? There are 2 unit capacitors there, 16 capacitors there. I didn't write now how much is the unit capacitance. I should have figured that out for you, I guess. And there is some, and that this is also something here. If you switch here the input of an input voltage, depending on the impedance here, you have kickback noise. Huh? It's easy to say that if you put switches in there as a flash A to D converter, then you're going to have a kickback noise unless this is a real low impedance. That's why you need a buffer on the input voltage, which is hard to do. So that means that there is some provision here to avoid the kickback noise. So there is a switch connected to the input to make sure that this is quiet when that charge is coming back from the capacitances. So this is one of the little things. All the pipeline A to D converters nowadays have little things to improve the resolution and or the speed. Calibration is always in there, and little things like, for example, that the strength of this paper is this, because this is exactly the same as before. Another one, which actually compensates harmonic distortion. Yes. Remember, we have to make an amplifier over a wide range. How do you do that? Well, you have distortion, yes. Compensate for distortion. Some funny tricks. Compensate for distortion. It's not easy to do. Lots of circuitry to do that. Okay. So that means that in all of those blocks, and you see each stage has a flash A to D converter and then the DAC here, multiply times 4. This is actually only 2 bits used, and again, and again, and again, and again. And then we have a flash at the end, of course. Everything is going to give you so many bits, but there is harmonic distortion correction. Not easy to do, huh? Okay, well, on the ISSC last year, now in the journal, it does allow you to go to 100 megasamples with this. Of the 40-bit, there is about 11.3 bit left, and the power is not that high for that kind of speed, giving you something like 0.25 picojoule per conversion step, which is not bad. But you see, there are always little tricks in there in order to get to the higher number of bits. Here is just kickback noise compensation, and here it's harmonic distortion correction. Harmonic distortion correction means that the third harmonic has to be, it's all fully differential of course, third harmonic has to be corrected for, which is not an easy thing to try. A very different kind of pipeline is a comparator-based one. Don't they all have comparators? Well, yes and no. This is different. I have to talk about that because this has been developed by the MIT guys and they keep on doing that and the performance is kind of good. Huh? What is this? Very different principle. This is nothing else than a switch cap circuit. You may have seen that already. You see an amplifier and switches and capacitors. So it's got to be a switch cap circuit. And you know what the problem is? Something I've mentioned several times already before. We have to wait 6-7 time constants before all those capacitors are decently charged up to the final voltage, settling time. Meaning that this is never going to work at high frequencies. Switch capacitive filters never work at high frequencies because we have those settling time problems. The slew rate is never sufficient and the gain bandwidth is never high enough to really charge those capacitances in a very short time. So what you get at the output here in the switch cap filter is that exponential, which is going to give you an output voltage after 7 time constants. You end up with the output voltage within 0.1% or something. How about with a comparator, because this is an amplifier, how about with a comparator switching in a current source that keeps the current which charges that capacitance constant until the end? So what we have here now is going to be a comparator that charges the capacitance with a constant current, and that gives you constant slope as you know, and then at the end it stops. If I put a lot of current in there, the time that I need to go there is shorter than the time that I need to go from there to there. So a comparator-based switch capacitor filter in the first place is actually a switch capacitor filter in which the amplifier is replaced by a comparator which drives a current source. And the current source, the nice thing about the current source is that it charges the capacitor with a constant current. Here the current charged in the capacitance gets smaller and smaller and smaller and smaller, and it takes forever to reach that final tail there. Whereas in here you have a constant current, it charges it with the same current and it takes less time because it charges that capacitance with the same current as here in the beginning. In here the current is large, okay? Well, here it's the same current, so that means that actually if I would draw it on the same scale, I would say if I took a current source with the same current as here, it would do like this, and it would take only this amount of time to charge these capacitors rather than this amount of time. So comparator-based pipeline ADCs are actually ADCs in which the switch capacitor principle is replaced by that times 2 amplifier, for example, is replaced by a comparator-based switch capacitor filter. How well does it work? Well, the initial one was not too bad. 0.38 is not too bad, isn't it? The speed and 10-bit probably, leaving only 7, 4.5 milliwatts. Yeah. But if you look at the most recent one, last year, yes, fully differential, of course. You do see those currents, the current sources sitting everywhere. You see those current sources. This is now a comparator or a zero crossing detector. What is a zero crossing detector comparator? Comparing to 0, huh? Well, if you look at this, and then of course a feedback loop, all current sources, this is one stage, this is the next stage, and the next stage, and the next stage, huh? So if you do that, you guess, yes, you get at very reasonable numbers, huh? So this is certainly a technique which is worth your attention. Replacing the switch capacitor filters by comparator-based filters. That's what it is, and current sources. And as a result, each of those stages of a pipeline is going to be using is going to be giving you a higher speed for the same power consumption, or less power consumption for the same speed as before. Yes, I kind of like that. Still many people doubt it, but once you get to numbers like this, it's beautiful. We are not at the level of SARS. As I've shown you, SARS go to a level of 5 to 15 femtojoule per conversion step. But they go to higher speeds, which are not possible or hardly possible with SARS. So yes, I like that. Good. Now what else can we do with those pipelines, which all look very similar, pipelines at the end with a flash? I can make real high speed A to D converters, which was the reserve to the flash A to D converters before. Because if I take a pipeline, a slow pipeline, compared to what I could do with a flash A to D converter, this is a slow pipeline, for example, and I allow that to work on a certain clock. Then I take another one, and this one is going to work a little bit later compared to this one. How can I determine that? I need a real high-speed clock sigma delta modulator. So one period of the high-speed clock, shall I take that 10 gigahertz? The clock of 10 gigahertz. 10 gigahertz in principle, that is 100. 1 gigahertz is 1 nanosecond, a tenth of a nanosecond. So this is a clock which is a tenth of a nanosecond later than this one, and this a tenth of a nanosecond later than this one, and again a low speed pipeline converter, and at the end I put them all together. This is like a high-speed A to D converter. Okay? So that means that indeed I have a clock which is real fast here. That was my 10 gigahertz, and all the other ones are delayed by a tenth of a nanosecond, which is not easy to do. Okay? I need an accurate delay in there. It can be done, an accurate delay, but then at least the advantage is that I have a large number of low speed with beautiful femtojoules, low speed AD converters, and in total I get a real high speed A to D converter. Does that work? Yeah. For example, 32 of those fellows in parallel, not 4 like this. This is only to illustrate the principle. If I take 32 pipeline converters, all of them delayed over a fraction of a nanosecond, and I take the outputs together, then I get something that goes to real nice numbers. 7-bit all the way up to here somewhere, for example, 1 gigasample per second. Is that doing worse or better than in Flash AD? Your number of picojoules is less. So yes, it's a good solution. 32 at 120, this is a pipeline at 125 megasamples per second. 32, I get 4 gigabits per second. It's not quite 8-bit, it's only 7 or a bit less depending on how far I go, but it's close to it. Where do I use those? Now we are talking about that corridor out. This is used, for example, those guys are all from Agilent. Digital scopes or Tektronix, sorry, both. Meaning that indeed that's where you need that. Lower resolution, real high speed, but of course it can't prevent you from trying to go a little bit higher. And this is a viable solution. Another one is 80 of those at 250. You see, this is all pipeline CMOS, can easily be done. You have to generate those delays, and of course that input block has to work at 20 gigasamples per second. CMOS 20 gigahertz for CMOS. You see, this solution, this was bi-CMOS, this was done in bipolar, or in gallium arsenide, or something else exotic. But once you get there, and you can generate those delays, this is low-speed stuff to get a real high-speed performance. Yeah. Time interleaved. You see that indeed it's not really 20. I still wonder why this guy called this 20, because by the time you're 20 there is not much left, but yeah, what's in the title? Specmanship is always around. Is that bad? No, 28 picojoule per conversion is typical for those high-speed ones. Those femtojoules are only for the low-speed realizations. High speed, you get in the picojoules. Okay? And you have to be able to have very little jitter, of course, because you need those little delays fairly reproducible. So too much jitter would kill that. Jitter means high power consumption. 9 watts, sure. Another one is this one here. You see that indeed we have something like, well, shall I take this one? 65 dBs is more than 5-6 bits. But you can't get much further than 1 gigahertz here, and here it's already, by the time you reach the 8 8 gigahertz input, you only get something like 42 divided by 6 is 7-bit. 7-bit is not too bad, huh? 7-bit for 8 gigahertz input. Okay. I forgot how many of those are in parallel here. I thought I had it. Maybe I should add it for next time. But you have the paper here, you can check for yourself. Huh? So those are realizations, parallel pipelines. So pipeline, and finally one sample and hold. I've talked about sample and hold, not easy to do. You can imagine when you make a circuit like this, for example, a sample and hold done at a frequency which is 20 gigahertz with the accuracy of 8-bit, 7-bit is not easy to do, because you need the accuracy and you need the speed at the same time, and you're not allowed to use a lot of power. That's the problem. But that's always the problem, power for accuracy and speed. So what can I say? So here is one. Clearly something like that is always going to have one transistor. And then the question is, how do I drive it? And the nice thing about this is that the VGS is going to be constant, because this is the same voltage as over there. You see that? You see that the VGS is kept constant. So in all those sample and holds, because of the low voltage, one thing is that you have to try to keep the VGS constant, and as a result the R-on is not modulated by the input signal. That's one thing. And then to put power in there to do it at high speed, of course. This is a nice sample and hold. But there are so many. So how can we compare all those A to D converters? Well, on what basis do you do that? One thing is for sure, the flash you can't beat, because it's only one step. All the other ones, pipelines, take n steps. Successive approximations, very similar. And of course the slowest one is the first one, that voltmeter type thing. That takes forever to get to 10 bits. It takes you 1,000 clock cycles. So it's all a question of resolution versus time. Now another thing in there is all of them suffer from mismatch. All of them suffer from mismatch. Meaning that if I try to figure out how I can exchange resolution for versus speed and versus power consumption, then actually when I take the simplest mismatch expression, this one here, that says that if I look at the differential pair, and we have used differential pairs in all those comparators, but also current mirrors, in all those differential pairs and all those comparators which are differential pairs, I know that the offset, the mismatch, is inversely proportional to the resistor size. And the resistor size, you feel that power consumption somehow is going to be in there. The proportionality constant is that Pellegrom factor, which improves versus technology. No more now, but before it was improving. So that means that actually if we take this expression here with a proportionality constant and we put the W in there, increasing the width of a transistor, means that the current is going to go up, and current means power consumption. Let's assume all the supply voltages are 1 volt. So actually this represents power, and the L determines the FT of your transistor. Remember, the FT of a transistor only has the channel length in there. There is a simple expression with the channel length squared. This is in the normal mobility region. In velocity saturation, the FT is inversely proportional to the channel length itself, but the channel length is always in there. So it is possible, and I will show you the expressions in just a moment, to show how inaccuracy or offset is linked to power conversion, to power dissipation, and to speed. So that means that for a certain technology, within a certain technology which sets the mismatch, we have a constant relationship between power consumption, speed, and the error in there. Power consumption, speed, and the accuracy. And if I plug in those values, and here it is, for mismatch, for example, well, for mismatch we have to figure out, we take, for example, 3 sigma of the offset itself. Dynamic range is the maximum voltage, let's take 1/2 volt peak, and then the offset corresponding to a certain technology. The capacitance of course has to do with total area. The capacitances are going to go in there because the capacitance also determines the power consumption. So the power consumption has to do with how much voltage I'm going to store on a capacitance and how many times I do that. In other words, I can derive how much power I need for a certain capacitance, for a certain voltage, and for a certain inaccuracy. And here is the expression. And the same can be done for noise. Eric Vitos did that. Calculating that indeed a certain dynamic range for a certain voltage and a certain amount of noise at a certain frequency. This is the power consumption you need to do something at a certain frequency with a certain signal to noise ratio. Here this is signal to distortion ratio, and there is signal to noise ratio. And when you plot those, you get those curves from Peter Kinget, saying that if you are looking for a 60 dB A to D converter, okay, 10-bit for example, that you will need a certain amount of power to do that up to a certain frequency. And if you look at noise as a limit, this is the amount. And if you look at mismatch, this is the amount. And if you look at the papers in the General Solid Circuits, there they are. So they are closer to this than to this. It's not very realistic to take noise as a limit to figure out how much power you will need for a A to D converter. You better take signal to distortion ratio and mismatch, then at least you're only a decade below of what you can do. So this is simply saying the same thing as in the beginning. You have to look at the figure of merit. If you are asked to do a SAR, for example, and you're asked to do that at less than 15 femtojoule per conversion, you're not able to do that. Where is the 15 femtojoule per conversion? Here it is, the 10-bit. And those, the SARs here, correspond to something like 10 femtojoule per conversion. This is again the watts divided by frequency. Here are the picojoules, and there are the number of steps. 1,000 steps, and there are the picojoules, as shown in that initial example. So this is all saying the same thing. So actually, when you look at A to D converters, where are the limits? And there is a beautiful graph picked from a very funny paper somewhere in the selected areas of communications some time ago, to show when you make AD converters, all those little red dots, and those are not recent ones, those are old ones, all seem to be limited. Yes. When you go low speed, like SARS for example, okay, you see that thermal noise is going to kill you, which is not the same that when you go to a flash A to D converter, then you are here somewhere, because then you are limited by the blue lines. What are the blue lines? The blue lines are jitter, aperture noise. And the 3 lines I have on there, you see we have 3 blue lines. One is taking into account aperture inaccuracy of 1 picosecond, half a picosecond, and 0.2 picoseconds. 0.2 picoseconds is this one here. This is this one. And this is the limit today when you look at the high-speed A to D converters. This is the limitation. Jitter is limiting you, whereas there is thermal noise. And there are some other things. If you go real high speed, this is ambiguity, is very similar as jitter. For example, Heisenberg is nowhere in the field. No, not yet. It's all thermal noise or jitter. And the matching, the mismatch is actually included in here too. So they should be on this place. So when I look back now at the curve I've shown you from the very beginning, you see now that indeed this is the same as before. When you look at the interpretation of Merman on his curves, it's always nice to hear what an author of a famous graph says about his own graph. When you look at this paper here on CICC a year ago, it's worth reading. He says, well, on the lower end here, what is the limitation? For signal to noise ratios below 75 dB. It's technology and power, but technology also, which includes mismatch. That's technology. Thermal noise is not technology. Technology means matching. And he says that indeed for the lower ends, like in SARS and all that, it's the matching of the capacitors that kills you. But technology goes up all the time. We go from 0.13 to 0.09 to 65, 45, etc., etc. The peak is now even lower. That means that indeed this gets better every year. Technology gets better every year. It's not quite doubling every second year. This ratio halves about every 1.6 years. This is improvement in technology. People working hard to go from 65 to 45. But if you look at the higher end, here, more than 75 dB, if you look over there, you see that there are less dots in this area. It's not because there is a frame there. There is nothing there. All the dots on the lower end are here. When you look at the higher end, Then, of course, it's limited by thermal noise and signal swing. And signal swing, the voltage is 1 volt, doesn't go down much the same. And thermal noise is just a question of power. You can't improve that. So having technologies following the path of more is not going to help you. Thermal noise is a basic limitation. And then you see that things improve only, this ratio only halves every 5 to 6 years. So it's not true when you plot that this improves all the time everywhere. No. The SARs are improving all the time because technology helps the mismatch. But everything that's high speed is not improving that much because it's limited by thermal noise and by jitter is also in there. And that improves only very slowly compared to SARs. And finally, ladies and gentlemen, what was given last week on the ISSCC 2010? Well, here it is. Even the numbers of the papers are on there. This is the 100 femtojoule per conversion step, and this is the 10 femtojoule per conversion step. And you see they didn't beat everybody else, because there is a dot there already from previous years and previous years and previous years. Those are the dots of this year. They're just in the middle of the cloud, I would say. So was it worth going over there? I don't think so. Sorry, it's always worth going over there, but as you can see, the realization of 2009s are in the same ballpark as the realizations of 2010. This, of course, is going to be included in Berman's graph if you wait a number of months, but this was made last week, and I couldn't resist the temptation to show you that. And this is what I wanted to show you about A to D converters, excluding oversampling, because that is next week. Thank you for your attention.